Good afternoon, everyone. Myself, Rahul Daya, and I am delighted to welcome you all to day 6 of the AICT ATAL Faculty Development Program on Next Generation Communication for 6G and beyond. We have successfully completed 5 days of highly enriching and impactful sessions. Today, we proceed with 4 more exciting and application-oriented sessions. After that, we will go for the quiz, and after that, feedback from the participants. We extend a warm welcome to all faculty members, research scholars, and participants joining us online from various institutions. Your active participation is truly appreciated. To begin today's session, it's my honor to introduce our first speaker, Professor Swaminathan R. He is an associate professor and head of the Department of Electrical Engineering at IIT Indore. He earned his PhD from IIT Kharagpur in 2016. From 2015 to 2019, Dr. Swaminathan served as a postdoctoral research fellow at NTU Singapore and later as a visiting faculty member there in July 2023 and 2024. He joined IIT Indore as an assistant professor in 2019 and has been an associate professor since October 2023. Dr. Swaminathan has authored and co-authored over 100 research publications, including journal articles, IEEE conference papers, book chapters, technology disclosure, patents, and a textbook. His research interests span wireless communications, communication systems, and coding theory. He has received several notable recognitions, including the Best Research Paper Award at IIT Indore in 2025 and being featured among the top 2% scientists in the world in 2025 in a global study by Stanford University, USA. In 2021, he was recognized as an exemplary reviewer by the IEEE Communication Society, USA, for his outstanding contributions to IEEE Communications Letters. He was also honored with the gold medal from the College of Engineering, Guinea Anna University, for academic excellence. Dr. Swaminathan has delivered numerous invited talks on entrepreneurship and wireless communication at premier engineering institutions. He actively contributes to the global research community as a reviewer for leading IEEE journals and as a technical program committee that is TPC members for major IEEE conferences. Professor Swaminathan will be speaking on the topic non-terrestrial network for next generation communication. Sir, we are delighted to have you. I request Professor Swaminathan to begin the session. The virtual stage is yours, sir.
Okay. Thank you so much. I hope my screen is visible.
Yes, sir. Screen is visible, sir.
Okay, presentation is also visible. Let me put it in the full
Yes,
screen. Just a minute. Yeah, full screen it is, right?
Yes, sir. Yes.
Fine. Okay. Okay.
Okay, thank you, sir.
So
can.
thank you. Mr. Rahul. And I also thank Professor Jaising for giving this opportunity to deliver this lecture. It's a very important lecture in the context of 6G wireless communication, so which is non-terrestrial networks, especially for next generation of communications, especially 6G. So we will go through this session maybe in a brief overview about non-terrestrial networks, as well as some specific research which we have carried out in our research labs as well. So the outline would be from the perspective of 6G communications, and then where the non-terrestrial networks is going to play an important role. Then we are going to see some introductions to various aerial platforms associated with the non-terrestrial networks. And with respect to our research group, we are working on the free space optics communication or optical wireless communication, especially in the context of non-terrestrial communication, non-terrestrial networks. And then whatever we have carried out, few of the basic works in the last 5 years, I will be presenting those works as well, along with some results. So that is what is the outline of today's talk. As you could have already seen, because this particular workshop is about the next generation communications, you would have maybe seen this particular the diagram which is flashed on the right side. where it gives an introduction to the various key performance indicators of 5G and how it is compared to that of the fourth generation of communications, where the outer concentric circle corresponds to that of the IMT 2020, which is 5G, and the inner concentric circle corresponds to 4G, which is IMT advanced. And you can see all these key performance indicators which have been mentioned over here, such as peak data rate, user experience data rate, spectrum efficiency, mobility, latency, and so on. As you can see, the enhancements with respect to the fifth generation of communications, say, for example, with respect to 5G communications, the peak data rate which is being targeted is around 20 Gbps compared to that of the 1 Gbps in the 4G, whereas the user experience data rate is of the order of 100 Mbps compared to that of 10 Mbps. And the latency, there is a huge reduction in the latency compared to that of the 4G's 10 milliseconds latency, whereas here it is 1 milliseconds. And the connection density is also increasing. That is the number of devices which can be connected per square kilometer, which is of the order of, say, 10 raised to power 6 compared to that of the 10 raised to power 5 devices per square kilometer, which was the target in the 4G. As you can see, this 5G is basically linked into three major usage scenarios. These KPIs also falls under some of these usage scenarios or use cases, which is what we call. And that three important use cases with respect to 5G is given over here, which is being mentioned as enhanced mobile broadband, EMBB, and then ultra reliable low latency communication, which is abbreviated as URLLC, and then the massive machine type communication, which is abbreviated as MMTC. And to give just a brief introduction about each of these usage scenarios, like enhanced mobile broadband is what is with respect to our mobile communications which we are having. So that is the usage scenario, which generally demands higher network capacity as well as a higher peak data rate. And some of the KPIs which is given over here corresponds to that of this enhanced mobile broadband scenario. For example, the peak data rate, user experience data rate is all connected with enhanced mobile broadband scenario. Similarly, ultra reliable low latency communications, this particular usage scenario, though it is being standardized, URLLC and MMTC is being standardized in 5G, which means you can see various specifications associated with these usage scenarios that has been standardized. If any industry is developing a product for these usage scenarios, they have to adhere to those specifications. So though it has been standardized, but URLLC and MMTC will not see much of the applications in the ground. Though there are niche applications and industries have started developing various applications, but much of the applications in the ground you would see mainly towards the EMBB scenario. All right. So URLLC is mainly, as the name implies, the scenario which demands ultra reliability and very low latency. So ultra reliability means it targets the packet error rate of about 10 raised about minus 6, or successful delivery of packet of the probability of 1 minus 10 raised about minus 6. 1 minus 10 raised about minus 6, you can see the success probability is of the order of 0.99999. Right. So the applications which demands that much of very high reliability as well as very low latency of the order of 1 millisecond. Say, for example, in the right-hand side diagram, the 1 millisecond latency which is being mentioned over here for 5G communication corresponds to URLLC. Okay, though the latency can be slightly relaxed for EMBB and MMTC scenario, but 1 millisecond latency which is being given over here is mainly towards URLLC sort of a scenarios. Okay, and the best example application scenarios for this URLLC use cases, you can claim this autonomous vehicle scenarios or factory automation scenarios, which all comes under the category of mission critical applications. Mission critical applications means pretty critical aspects. If there is a the higher packet error rate, or if there is a compromise in the if there is a compromise in the delay aspect, then these applications basically the outcome would be pretty bad, basically, right? So when you're having a compromise on it, when you have either compromise on the reliability or on the latency, the outcome will be pretty bad, right? Especially autonomous vehicles, right? So autonomous vehicles are self-driving cars. The people are envisioning. So where the reliability should be very high and the latency delay in delivering the packet should be very less, then only it would be feasible, practically feasible. Or otherwise, the vehicle will be at risk, as well as the person who would be sitting inside the vehicle will also be at risk. So that is why it is critical. That is why we call that as a mission critical applications, right? Those applications demands a very high reliability and very low latency, as I have mentioned. Then the third usage scenario is massive machine type communication. Massive machine type communication, where here in the right hand side, where you can see this connection density, right? That is the number of devices which can be connected per kilometer square. That connection density corresponds to that of the MMTC scenario. Okay, it may not be for an EMBB or URLLC scenarios, right? It cannot be for number of mobile devices. Of course, number of mobile devices cannot be of the order of 10 raised to the power 6 devices per square kilometer. No, you cannot do a very practically feasible resource allocation for mobile devices, especially which comes under the category of EMBB scenario. Whereas massive mission type communication, which is like a small IoT sort of nodes, basically the applications which comes under this MMTC is IoT. Everyone knows this, that Internet of Things. The small IoT based nodes, right? Small nodes in the sense they basically the target data rate, which will be of the order of few kbps only, and there can be slight compromise in the delay as well. And then so those kind of small sensor nodes, because they're going to sense some sort of a data, and they're going to transmit to the edge node or the cloud network or to the nearby base station and so on, right? So that's mainly for monitoring purpose, not for critical applications, mainly for some sort of a monitoring. So that there the delay can be compromised, or even the data rate requirements may not be too much, where the main thing is the connection density. You might need to deploy so many such devices per kilometer square for efficient monitoring of, say, air quality monitoring, soil quality monitoring, and so on, right? So the main the KPI which deals with this MMTC is this connection density, where at least we should be targeting 10 raised to the power 6 devices per square kilometer. And these sort of small IoT devices demands very high energy efficiency. They should be energy efficient, where the mobile the user terminal in the EMBB scenario or URLC scenario need not be so much of need not be so energy efficient. Okay, but for MMTC, the main thing is those small IoT nodes should be very much energy efficient. So energy efficiency is a key indicator over there. So for each of these usage scenarios, you can see there are critical key performance indicators which has to be met. Say, for example, enhanced mobile broadband, it is more of network capacity and peak data rate, and as well as user experience data rate. Ultra reliable low latency communication, the reliability and the latency plays a vital role over there. And then massive machine type communication, there you can able to see the connection density and the energy efficiency should be pretty much high over there. So you can see the varying requirements with respect to that of the 5G. That is what is the main difference with which the 5G is being proposed compared to that of the fourth generation of communication. In fourth generation of communication, you are having the only usage scenario, which is mobile broadband. That's it. Right? In 5G, you are being given with, or the 5G is being standardized with, of course, what is there in the ground is pretty different, because that is mainly for business reasons and commercial reasons. Still, we are going ahead only with one of the usage scenario, which is enhanced mobile broadband. Though the other two usage scenarios have been not explored too much, and industries are working around to explore this as well. But at least 5G give a provision for three usage scenarios, which is EMBB, URLLC, and massive machine type communications, right? So that is what 5G. That is how we differentiate 5G compared to that of the earlier generation of communications. And there the concept of network slicing will come into picture, because the same network, you have to slice it. Okay, because the demand for each of these scenarios are different. The resource allocation will be different. The bandwidth allocation will be different, right? One needs to be very much energy efficient, other need not be so. So you can able to effectively see the resource allocation will be pretty different compared to that of the fourth generation of communication, where it is the only usage scenario, and the entire network is mainly for that particular usage scenario. Whereas over here, the 5G network needs to be sliced. That is why the concept of network slicing is coming into picture, where the 5G network has to be sliced according to these usage scenarios. Okay, so that is what is that. Now, moving ahead, compared to that of the 5G, the sixth generation of communications, of course, whatever not being potentially explored in 5G definitely would be carrying over to 6G as well. In addition to it, in the sixth generation of communication, the main target usage scenario or use case, which they say is the first one, okay, which is a slightly revised version of the use case EMBB, which has been proposed in the 5G. Okay, EMBB is enhanced mobile broadband. But in 6G, what they are trying to propose is slightly an updated version of that EMBB, which you call it as ubiquitous mobile ultra broadband. Okay, that EMBB is being renamed as ubiquitous mobile ultra broadband. Now, the word, of course, mobile ultra broadband means, of course, very higher enhancements in terms of the data rates. That is what it is saying. But the first word is what will make our lecture pretty easy, where your entire non-terrestrial networks and everything is connected to the term which is very important, which is called as ubiquitous. Ubiquitous means it is everywhere, right? You need to have this connectivity everywhere. That is how rural connectivity, remote connectivity, deep sea communications, and so on, which has not been explored in fifth generation, or I should put it in this way, which has not been standardized in fifth generation of communications. They are trying to target those application scenarios. That is why the term ubiquitous plays a pretty or a vital role in the sixth generation of communication, especially to achieve this ubiquitous connectivity, right? This non-terrestrial networks plays a vital. Okay, so NTN is the abbreviation, and then and to give you a brief background about the recent 3GPP meetings which has been held, and one of the meeting, I hope you might be knowing, one of the 3GPP global meetings, which usually the standardization meeting, which they usually organize, it was held in the one of the meetings held in India, in Bangalore, basically in the month of August. So I happened to attend that meetings where various industry partners and the standardization the standardization organizations, they usually come together and propose various things towards 5G as well as towards sixth generation of communication as well, because sixth generation of communication as of now it is still in the study group stage, whereas in fifth generation it is more of working groups. And the lot of proposals have come in the domain of non-terrestrial networks, one. And the second domain, which is of huge interest in sixth generation of communication, is ISAC, which is integrated sensing and communication. So these two things unanimously we have seen, like I have observed, a lot of organizations have come up with so much of proposals. Even one of that, the slides or the one which is presented by Nokia, I have also got those slides. Maybe what they are targeting in sixth generation, I have also included that for the information. So this NTN and ISAC are going to be some of these two of the key technologies which is going to play a vital role in sixth generation of communication. Because the main motivation behind NTN is, of course, it is very expensive to have a worldwide connectivity, especially only using your terrestrial networks for the areas, for the remote areas, which is having a very scarce population. So the NTNs would be playing a vital role, where these NTNs will be supported by various aerial platforms. The aerial platforms, there are various types of aerial platforms we will also be seeing, such as drone, UAV, and then HAPS, which they abbreviate, which is called as high altitude platform station or high altitude pseudo satellite. Even the satellite is also one of the aerial platforms. Basically, this NTNs is going to be supported by various aerial platforms, and then this will help in providing the connectivity anywhere and everywhere. That is how it is linked to the term ubiquitous. Okay, and so in the 6G networks, apart from the data, which would be the data transmission will be also be over the vertical heterogeneous networks. Vertical heterogeneous networks means from the ground node, it goes to one of the NTN terminals. It can be UAV, HAPS, or to the satellite, and then it comes back to the ground and so on. So the data transmission, unlike the earlier generation of communication till 5G, next generation of communication, more or less, they are going to explore the vertical heterogeneous networks, where three of the important layers in the atmosphere are going to be interlinked. That is the ground networks, the aerial networks, and the space networks. Basically, space networks deals with a lot of satellites, LEO, GEO, MEO satellites. Aerial networks is going to be dealt with a lot of platforms such as UAVs, high altitude platform stations, and so on. And the ground networks are going to be various terrestrial networks. So this integration of these three networks, that is the ground network, aerial network, and the space networks, is going to happen in this. It is envisioned that it is going to be happen. It is going to happen in the sixth generation of communication, and that is why NTN they will also be termed as space, air, ground integrated networks. There's also another equivalent term for this, which is space, air, ground, SAG networks, or sometimes they can call it as SAGIN, which is space, air, ground integrated networks. Okay, so it is being at least thought that by integrating this, they could able to achieve this ubiquitous mobile ultra broadband services, which is one of the usage scenarios which has been listed in sixth generation of communication. And the various releases, which is over there, release 17, 18, 19, various efforts have been made by organizations towards this NTN. Say, for example, in release 17, they introduced an initial support for this NTN as a part of 5G NR, including LEO satellite integration, that is satellite integration for both IoT and new radio-based systems. Then it focused on basic satellite channel modeling, delay handling, Doppler shift compensation, as well as transparent payloads. There are two types of NTN architectures, transparent payloads and the payload regeneration architectures, that we will see quickly. Okay, that is why I have highlighted these terms. In the release 18, they expanded this NTN support under the 5G advanced umbrella, and the enhancements include relay-based NTN, which is called as payload regeneration, and then improvements in mobility, beam management, and then support for higher frequency bands. So another sort of study came up in the release 18 as well as in the release 19, which is ongoing, that aims to mature NTN for commercial deployment. It is focusing on interoperability with terrestrial networks, supports for high altitude platform stations, direct to handset communication. Direct to handset means satellite to handset communications, as well as multi-layered NTN architectures. Multi-layered means like first level layer will be aerial and the second will be space and so on. Multi-layered NTN architectures. All this has been explored and various technical proposals have been received from the organizations, and it has been discussed and deliberated in these releases. And to give you some overview of what are the potential bands in the NTN. NTN, of course, like in 5G, we have FR1 and FR2, even though FR2 is being in low priority now. FR2 is what is your millimeter wave band. That is, you can see over here about 20, you can see the about 17, 20 gigahertz, 30 gigahertz, around that. You call it as FR2, which is basically just being mentioned as like 24.2 gigahertz to 52.6 gigahertz. That is the FR2 frequency. And below that, you would have this FR1, though usually they call a sub 6 gigahertz as FR1. But still, they are exploring 7 gigahertz band as well in the 5G and 6th generation of communications, right? That is why they call it as FR1. So basically, they have identified 45 bands in the FR1 and 4 bands in the FR2 for potential implementation of this NTN, which has been listed over here, where you can see the top 2 bands. 1.9 gigahertz, 2 gigahertz, 1.6 gigahertz, all that corresponds to a FR1 band. And FR2 band, as you can see, 27, 20 gigahertz to 30 gigahertz band in the FR2. That has been identified as the potential NTN bands. Of course, FR1 is being of a higher priority. In FR2, there are a lot of challenges, especially the millimeter wave communication, especially to handle the Doppler and the Doppler shift, as well as the requirement of more or less like a line of sight scenario for the millimeter wave communication. These are all a lot of challenges concerned to that. And this is how basically I'll give an introduction to how a satellite phone or satellite connectivity works. Then we can look into the updated architecture corresponding to that of the NTN scenario. Usually we'll have a satellite phone, which instead of connecting directly to the terrestrial base station, sometimes the satellite phone directly connects to the satellite, or via the terrestrial base station, it gets connected to the satellite. And from the satellite, it goes to a satellite gateway, which will be located in the earth. And then it goes to the internet connectivity or the core network. Unlike from the base station, you have your distributed unit, central unit, CUDU, and then from the CUDU to the 5G core. Instead of that, you have this sort of connectivity directly to the satellite, and from the satellite to the gateway, then to your core network. This would be possible, especially where the areas where it is pretty much challenge, where there is a challenge in deploying this microwave or optical fiber cable, because most of these the core network, right, from the access to the core network side, it is all connected with your fiber basically. So when you have challenges in deploying those things, then your satellite backhaul, where the backhaul connectivity is mainly based on satellite, your satellite backhaul connectivity will come into picture. And this is how they are describing this NTN connection. So there are various terms associated. One is the NTN gateway, another one is NTN terminal, NTN platform, then there is something called feeder link, and then the service link. Right. So NTN terminal means that refers to any 3GPP user equipment, which is mobile or any other user equipment, which is what they call it as an NTN terminal. And then NTN gateway is a logical node connecting the NTN platform with the 5G network. So you have a 5G mobile network. To connect to that 5G network, you need an NTN gateway. That is like in the earlier architecture, you can see this satellite gateway, right? That is the NTN gateway, which is located in the ground, which connects your NTN platform, which can be either a satellite or an unmanned aerial system. NTN platform can be a satellite or an unmanned aerial system. It can be either a UAV or a HAPS or a satellite. Okay, so basically that is the NTN platform. To connect this NTN platform to this 5G network, you need a gateway. And service link is the radio link between this NTN terminal, ground terminal, and the NTN platform, whereas the feeder link is the radio link between this NTN gateway and the NTN platform. This is how a typical an NTN architecture, which is what they are proposing. So you can see a conventional 5G architecture in this particular slide. The upper diagram, which is over here, that is mainly towards this conventional 5G architecture, where user equipment is connected to G node B, then to a 5G core. That is how the conventional architecture. Now, how this architecture is being slightly modified with respect to NTN, where you can see where the place where you don't have a deployment or a deployment challenges, where you have with respect to deploying G node B, where you can see user equipment directly connected to a satellite, and from the satellite via the feeder link, it connects to an NTN gateway, and from the gateway, it is connected to a G node B, then to a 5G core. Right. So this is one architecture where you call that as a transparent architecture, where much of the processing will not happen over here, which will be simply a relay-based terminal. It would be the satellite, which is over here, it will be simply a relay-based terminal. Not much of the processing will be happening over here. That is why they call it as a transparent architecture. So where user equipment to the NTN terminal and then back to the G node B via the NTN gateway, then you will have your 5G core, right? This is the transparent architecture, which is they call it as bent pipe architecture. And the other architecture is, this is also equivalent to that of the term which I mentioned earlier, which is called as the transparent payload, which I mentioned, right? So transparent payload. And the other one is a regenerative payload, where you can able to see that directly the user equipment is connected to the satellite, and satellite to NTN gateway, and then to the 5G core network, where you can see the entire operations of your G node B is being observed in your satellite itself, or your NTN platform. That is what we call now in the NTN platform. Yes, NTN platform itself. Your G node B and everything is over this NTN platform. There is no separate G node B or your base station. Of course, those who don't know, of course, now you should be knowing, like G node B is called as a base station, especially in the 5G's architecture. Right. So you can see that is the next, maybe an advanced architecture, which they call it as a regenerative payload or regenerative architecture. So transparent, where you still have a G node B, only this is more of like a relay with a simple processing, not a heavy computation would be happening in your NTN platform. Via NTN gateway gets linked to the G node B. So this is mainly where the place you have deployment challenges of your G node B. The other advanced architecture is regenerative, where a lot of processing, because entire G node B's processing is happening in your NTN NTN platform itself, right? Either it can be via the NTN platform directly to the ground gateway to the 5G network, or it can be between the inter-satellite link or inter-NTN platform link, either from one satellite to another satellite to directly user equipment. That is also allowed, because anyway the G node B's functioning is being observed inside the NTN platform. These are the two architectures basically which is being proposed in those one of these in one of the proposals, basically, which they are looking aligning to these sort of architectures. So this particular figure captures the entire applications or the usage scenarios where this interconnection of these ground or terrestrial networks, the aerial networks, and the satellite networks will be helpful for various applications. It is mainly towards this your mobile communication scenarios, your disaster management scenarios, your agricultural scenarios, or your maritime communications, that is deep sea communications, and so on, where you can see a lot of the architectures or a lot of the integrations are happening here between this space networks, aerial networks, and this ground network. So this is one particular figure which captures the essence of this non-terrestrial networks. We will see at least individual advantages and the drawbacks or challenges of various aerial platforms, because where there are various shapes you can see over here, right? This is exactly the flight. Above this, the aircraft, you are seeing various hot air balloon kind of a structure, a bird kind of a structure, airship kind of a structure. You can see these are all the typical aerial platforms. We are going to see each and one by one each of these aerial platforms. Before going into the different types of aerial platforms and its advantages and challenges, you can see mainly the main advantages of deploying an aerial platform, let it be a UAV or let it be HAPS, it could able to provide you a line of sight link. Okay, for the ground node, always an aerial platform without much of a shadowing, it could able to provide you a line of sight link. So if it is a line of sight link, then it of course, as you know, it provides a highly reliable transmission over long distances, as well as some of these aerial platforms, say such as UAV or something, especially in terms of a disaster management sort of a scenario where your ground base stations have been damaged and you require some sort of a disaster recovery network. In those cases, you can rely on these aerial platforms, and the main advantage in that particular context is the dynamic deployment. That is, these aerial platforms can be dynamically deployed according to the requirements and the different, and it can be allocated to different users, basically. So the dynamic deployment is the second major advantage of these aerial platforms. As well as this multiple aerial platform networks, they offer ubiquitous connectivity to the ground users. They offer various connectivity to these ground networks. Multiple such aerial platforms or multi-layered aerial platforms, it offers a ubiquitous connectivity. And other advantages includes medium operational cost, ease of maintenance, and environmental friendliness, and so on. So these sort of architectures, as I've already mentioned, they play a vital role in network service recovery, especially in a disaster-prone region. And this either these aerial platforms, as I have already mentioned in the architecture, they are going to be either simply going to function as a relay station or even the aerial base station. That is, the base station functionalities, even it can be observed inside this aerial platform, or it is going to simply perform the operations of a relay. So there are two ways with which it can be looked into it. The first, the aerial platform, which everyone knows, or the important aerial platform which we will come across first, is this unmanned, or otherwise you can say uncrewed aerial vehicle, which is UAV, and usually it operates at low altitudes of a few hundreds of meter and a few hundreds of meter height, and with a coverage radius of about few kilometers, and ease of deployment, and it is battery powered. Usually it cannot be used for a longer period of time, maybe for a few minutes to a few hours is what is the battery life. And that's what, because it is having a battery limitation, there is always this UAV is going to be established mainly for a temporary or specific communication networks, especially for disaster recovery sort of networks. You can use it for some period of time. So that is how it cannot be a permanently deployed or the one which has a good battery backup. No, it cannot be used for those sort of an applications. Mainly for a temporary network service recovery sort of an applications, you can use this UAV. Again, the same advantage as I have already mentioned, dynamic deployment and the establishment of a line of sight communication with respect to the ground node. You can see this usage scenarios can be emergency communication, rapid network recovery, and so on. That is what is the usage scenarios of this particular UAV. So two example scenarios have been mentioned over here. One is the rapid service recovery after the base station infrastructure is being damaged. So this cross implies a malfunctioning base station. So then the user terminals can be directly connected to your UAV and then to a ground gateway to the core network. Okay, so that's how you can envision the first usage scenario. The second one is the base station offloading. Base station offloading means, of course, the base station is not malfunctioning, but it is being overloaded because maybe on one and off, like on an off time, maybe suddenly if you are having a stadium nearby, the base station is nearby a particular stadium where a big match is happening, where the heavy, like huge crowd is being inside that particular stadium, then the nearby base stations would get overloaded. So then, especially to ease out the network, then you can have you can offload some of the tasks to that of the UAV. So in addition to that of the base station, which is being overloaded, you can also deploy this UAV, which functions the some of the role of the base station, and it could able to facilitate the communication signals for various user terminals located in the ground. So because of the overloaded base station, these aerial platform, that is UAV, can complement or supplement the functions of these base stations. That is why we call that as a base station offloading. And the scenario is especially in extremely crowded scenarios, right? So these two are the two example scenarios where you can deploy UAV. The other ones are mainly for the terrain challenging. If there is a terrain where the base station networks deployment is having a challenge, as I have already mentioned. So to connect it to the end user, you can deploy as many as UAVs or aerial platforms, and this functions as basically a relay-based relay station. That is one thing, and as well as it will also be helpful for this agricultural scenarios as well, which is UAV aided information dissemination and data collection, especially for IoT sort of scenarios. This UAVs are deployed mainly to collect information from a large number of wireless devices or disseminate information to a large number of wireless devices, especially in precision agricultural based applications. These are all various applications of this UAV, either the UAV functioning as a relay or the UAV functioning or supplementing the base station, or even functioning the role of an aerial base station, or it is being simply information dissemination and data collection based terminal for precision agricultural based applications. So these are all the three, at least the various usage scenarios of this UAV. Next, the high altitude platform station, that is HAPS. High altitude platform stations are also otherwise called as high altitude pseudo satellite, and that is going to play a vital role in the NTN. And what is a HAPS? It is nothing but a quasi-stationary aerial platform. Especially it operates in the stratosphere layer of the atmosphere, and the stratosphere layer is usually located, which is 17 to 25 kilometers above the Earth's surface. Right, 17 to 25 kilometers above the Earth's surface is what is the stratosphere. right? The next layer of the atmosphere it will be stationed there, right? That is why the impact of atmospheric distortions or something is pretty less, especially on the HAPS. So that is why we can station it more or less. It may not be maybe in a particular position you can station it without much of a problem. That is why you call that as a quasi stationary aerial platforms. And it has a capability to provide a wider coverage compared to that of your UAV, because UAV is being deployed in the height of, say, a few hundreds of meters in the atmosphere, whereas this HAPS is being located in 70 to 25 kilometers. Remember this height, right? So hence, it basically, the name itself implies, right, the other name for the other expansion for HAPS, which is high altitude pseudo satellite. So of course, it is a pseudo satellite. It basically functions like a satellite, right, which provides a wider coverage, as well as it slightly there is a flexibility to move rapidly in emergency situations compared to that of the satellite. So that is why this is going to be very important. Basically, it is in between your UAV and your satellite, right? So that is why it is pretty much important, especially in the aerial networks. And there are some challenges as well, and the immature airship technology, because nowadays there are few of the startups who are working developing this airship, but it is in the early stage now. So immature airship technology, necessity of monitoring the station and stabilization of the onboard antenna, these are all some of the challenges, but still many of them are working out for the deployment of this HAPS. These HAPS are usually classified as unmanned airship and unmanned aircraft. Okay, unmanned airship as such. You can see this Google Loon example I have given, which is like on the left side, which is there, a semi-rigid propulsion system and can carry a payload of about 1,000 to 2,000 kilograms, and which is solar powered and designed to stay more than 5 years within 1 kilometer cube position. Within 1 kilometer cube position, it can be designed. It can be designed to stay for more than 5 years, which can carry a payload of 1,000 to 2,000 kilograms, and it is being solar powered. Okay, that is what it is, unmanned airship. And the other one is an unmanned aircraft, which is on the right hand side, which is Airbus Zephyr. These are all some of the airships and the aircraft that is like equivalent to HAPS, you can say, that has been developed by various giants, the industry giants, which is like Google, Airbus, and so on. For some niche applications, these are being targeted, or they are trying to leverage these platforms, especially for our non-terrestrial networks. The unmanned aircraft, which is over there, that is again solar cell mounted, which is solar powered, especially on the wings of the mounted on the wings, basically, and it carries a payload of about 50 to 300 kilograms, and the flying time is of the order of several months. Okay, whereas the unmanned airship is of the order of more than 5 years. It carries a huge payload. Here, the payload capability is slightly less, as well as the flying time is of the order of several months. These are all some of the classifications or different types of your aerial platforms. So now we will move into some of the aspects which we have worked, where we linked the optical wireless communication with respect to that of the NTN. This is mainly the research works which we have carried out in the last 5 years, and I'm going to present some glimpse of it, because this NTN terminals could able to establish a line of sight connection with respect to either the satellite or with respect to the ground node. So instead of having an RF based communication, why can't you rely on an optical wireless communication, which requires a line of sight communication, right? To deploy an optical wireless communication, you need a line of sight scenario between the transmitter and receiver, or the transmit aperture and receive aperture has to see each other, basically, to establish a line of sight connection. And instead of RF based communication, why can't we deploy a free space optics communication, is what is the thought process, especially from the NTN scenario, connecting a ground station with respect to an NTN terminal, which is like a HAPS, and from the HAPS to that of the satellite. Why can't you rely mainly on a free space optics communication, and how you can evaluate the performance, what would be the performance gain, and so on. This is what is the motivation towards going towards this free space optics communication for those who are new to this particular term, FSO or optical wireless, I'll give you a brief introduction about it. Because your RF communication is capacity limited and it is also costly as most of the frequency bands are licensed. So the demand for, as well as the demand for the RF spectrum is keep on increasing with the growing popularity of new wireless devices. And several data heavy wireless devices nowadays demand a lot of huge data rates and so on. People have started working out, looking for other possible options for wireless communication. That's how a growing interest has been witnessed in the research and development of optical wireless communications, especially in these three major brands, which is infrared, visible, and ultraviolet frequency bands, right? So the last decade or more, a lot of research work has been going into this optical wireless communication. Under this optical wireless communication, two main technology which is coming inside this, the free space optics communication, and the other one is visible light communication. As the name implies, if the optical wireless communication is in this visible light frequency band, then you call it as a visible light communication. And suppose if the optical wireless communication is in the near infrared frequency band, you call it as a free space optic communication. So visible light communication is mainly restricted inside a indoor wireless scenario, which is mainly indoor communication, as well as free space optics communication, which operates over the near infrared frequency range. It is mainly for the outdoor communications, right? And of course, there is a third optical wireless technology based on ultraviolet frequency band, which is called as ultraviolet non-line of sight communication, UVNLOS communication. Of course, maybe 5-6 years before, it was also in various researchers have also working towards that. But nowadays, because of the nature of the frequency band, ultraviolet radiations and other things, maybe I'm not very sure. A lot of works are not going into this ultraviolet frequency bands, where major works are being focused towards FSO and the VLC. So VLC, the best example for visible light communication is that Li-Fi, which you'd be hearing, right? The complementary to Wi-Fi, right? Wi-Fi is mainly an RF communication based, whereas Li-Fi is more of light-based communication, right? All right. So the typical example for VLC is your Li-Fi. As I've already mentioned, FSO, it is mainly for optical wireless communication in outdoor scenario, and it refers to the line of sight connection between two fixed points. Of course, FSO can be established between two fixed points in the ground node, okay? Ground node or between the ground node to the aerial platform, but the node should be more or less fixed. If one of the nodes are moving, then it will be a problem to establish a line of sight connection because it is a light-based communication. So the line of sight requirement is a basic requirement. That is why you cannot, it is very impractical. It is not practically feasible to deploy an FSO communication between say a mobile terminal and the base station. So that is not a feasible option because the mobile terminal will be moving, and it is very, very difficult to establish, though there are pointing acquisition and tracking mechanisms available to align this link. But that may work for maybe for a reasonably whenever there is a small movement which is happening, then these fat kind of equipment can come into picture for acquisition and tracking. Whereas you cannot definitely deploy an FSO communication between a moving terminal of a particular speed and the base station. No, you cannot deploy that. It is very, very challenging. The main advantage is why the people are moving towards this or exploring this optical wireless communication is because it supports a very high data rate of the order of Gbps over a short range transmission. And because of the availability of license-free optical carriers, people are also looking towards this as a potential option because it is operating in over a near infrared band, right? So it is of the order of terahertz band. So you can easily get gigahertz type of a bandwidth, and you can 100 gigahertz type of a bandwidth, and you can able to enhance the speed up to Gbps. So these are all pretty easier, especially in FSO communication. Of course, there are limitations, as I already mentioned. It works only for short range transmission up to a few kilometers. So especially your backhaul network, instead of optical fiber, you can think of replacing with FSO communication for a short range. So there are a few limitations associated, which we will see. Yes, operating frequency, of course, FSO uses basically a narrow lasers. Basically, the laser would be the transmitter, and the photon detector can be the potential detectors, which can be over there. Of course, FSO operates over laser. In terms of BLC, your LED will be functioning as a transmitter in the visible light communication, whereas laser will be functioning as a transmitter in case of an FSO communication. Operates above a frequency of say 100 gigahertz near infrared frequency band in electromagnetic spectrum. So 100 gigahertz. So that is why I'm saying, so easily you can get tens of gigahertz bandwidth, and easily you can able to get a Gbps speed. And the wavelength range is of this much, that is 700 nanometer, 1600 nanometer. And you can see the bandwidth ranging from 100 gigahertz. This is now you can compare it with the RF wavelengths. That's why I'm saying RF wavelength is of the order of millimeter, right? 30 millimeter to 3 meter, whereas you can see it is nanometers. Okay, and the RF bandwidth availability is of the order of at least maximum 1 gigahertz bandwidth is being proposed in 5G in the FR2 frequency range. Provided you are operating in millimeter wave, then only the maximum bandwidth which they are proposing is of the order of 1 gigahertz. Otherwise, in FR1 itself, what they are targeting is of the order of 100 megahertz. That is itself is the maximum bandwidth. Now you can see the bandwidth which you can get from the free space optics communication. That is why it is an emerging alternative to that of the RF systems. Apart from the one which I mentioned, which is like a data rate advantage and analyzed spectrum, there is also other the two advantages. One is the spatial confinement. Spatial confinement means you have a very high reuse factor because you don't have much interference. Cross interference you may not be facing because it is more of a narrow laser beam which is being focused towards that of the receiver. So you can deploy parallel links without bothering about the interference, unlike your RF-based communication. That is why we call it as a spatial confinement, as well as it is ease of deployment, which is compared to that of the optical fiber. So it is a flexible connectivity you can provide without need to dig, lay, and maintain these underground cables, which is being given in this animations, just being on the right-hand side. You can see an optical fiber where you have to spend a lot in deploying it, whereas in FSO, it is just you aim and then connect over the top of the buildings. Okay, so that is why it is I have mentioned it as a ease of deployment, especially in the context of comparing it with the optical fiber based communication. Applications is so basically it can be used for surveillance monitoring, inter-campus connectivity, and then because surveillance and monitoring also, it is mainly because the security aspects is also pretty good. It is highly secured link. The moment it is being tapped, you can easily come to know because it is more of a line of sight link. It is very difficult to tap the link that is an eavesdropper to basically tap this link, especially the FSO link is concerned. And backhaul applications, you can see either the backhaul links for remote connectivity. You can see a remote hill having a base station and then another remote island, another base station, but with using a central controller. If you have a direct line of sight, which is available of the order of few tens of kilometers, especially you can deploy a free space optics communication. Then backhaul links for your cellular base station, especially from the macro cell base station to that of the central controller. So you can deploy a free space optics communication, or even you can see a ground to satellite, inter-satellite link, satellite to your aerial networks. So inter-HAPS link, inter-UAV links, and so on, where you can, especially for deep space sort of a communication, you can also deploy this free space optics communication. Coming into the FSO communication for space air ground integrated networks, as I've already mentioned. So since in the NTN or a space air ground integrated networks, you have at least some fixed ground nodes, say such as a base station or a gateway node, and you have a fixed HAPS because it is quasi-stationary, and you're more or less in your concerning with your satellite also, you can able to deploy your FSO communication, especially between these fixed nodes, especially fixed ground station and HAPS, and the HAPS to that of the satellite and so on. You can there is a there's a huge potential to deploy these optical wireless links, which have been mentioned over here, where you can see in the backhaul solutions where your base station, apart from the base station, your cellular user terminal is connected to the base station, and from the base station to that of the satellite. That is one of the transparent architecture which I was mentioning. Now, instead of having an RF based communication, you can have an FSO based communication between the NTN terminal and the base station, that is the G node B or the gateway over there, because those are all fixed nodes, so you can easily have uh, a free space optics communication link. Okay, and for the disaster recovery, all that, where if the ground station is fixed, you can connect any of your NTN terminals, especially HAPS or satellite or UAV. Predominantly, if they are quasi-stationary, then instead of an RF-based communication, you can, as an alternative which we are providing, is an FSO-based communication can also be deployed, especially for providing a huge data rate. Okay, where you can again you can see an FSO gateway to the ground, to that of the satellite, from satellite to that of the HAPS to that of the base station. So this is like a connection between the base station and a remote core network via a multi-layered NTN architectures. You can have it using an FSO link, right? So these are potential scenarios where you can leverage the free space optics communication. So here, maybe for the next 15 minutes or 20 minutes or so. So I'll present some of the basic system model which we worked, and maybe some of the channel models which we have used for FSO communications concerning this basic system model. This particular system model which we worked maybe 4 years ago, and it was published in Transactions on Aerospace and Electronic Systems. It's a basic system model where a ground HAPS, that is aerial, and the satellite network is being linked with the help of an FSO communication. As you can see, ground station to HAPS is through FSO communication, and HAPS to that of the satellite is through another FSO communication. Where from the ground station to HAPS, we supported this FSO communication along with the backup RF link as well, because this FSO communication is having three major anomalies, okay, which I will mention. So in case if there is a failure in the FSO link, then it would switch over to that of the backup RF link. Okay, that is why a hybrid link is being targeted between ground station and HAPS. And ground station and the HAPS is what is the link which is sensitive to more channel distortions, because that is where your entire atmospheric distortions would be coming into play. Okay. However, since HAPS is in the stratosphere, which is above this atmospheric layer, and your optical beam between your HAPS and satellite is free of these channel distortions, because your atmospheric layer is over. Stratosphere to satellite is more of that link is very less sensitive to channel distortions. That is why we maintain only the FSO link between the HAPS and satellite, whereas from the ground station to that of the HAPS, we considered a hybrid link between your ground station and the HAPS. Okay, because the link is more sensitive to channel distortion. So the priority will be given to FSO link. And if the FSO link, if there is a failure or if there is a degradation in the quality with respect to the FSO link, it will switch over to that of the RF link between the ground station and the HAPS. From the HAPS to that of the satellite, it is more of a direct FSO communication. That is an optical wireless link. And this HAPS is being functioning as a relay. It is functioning as a decode and forward relay in this particular architecture. So the first phase transmission will be source to relay over the FSO link. And in case if the FSO link quality is pretty good, that you can check it by checking the instantaneous SNR at the relay. If the instantaneous SNR is satisfactory, then you decode the information, re-encode it, and forward it using the FSO link in the satellite. Suppose if the instantaneous SNR or the quality is pretty bad, then you can, using a feedback link, we can request the base station to use it over to transmit the information over the RF link and get the information over the RF link, then decode it, re-encode it, and transmit via FSO link to that of the satellite. So that is why I mentioned a switching scheme here. There are 2 to 3 potential switching schemes, but what I'm mentioning over here is 2 of the schemes which are very important. One is called as a hard switching. Hard switching is if you will first transmit over FSO link, if the link is satisfactory. Otherwise, if your instantaneous SNR is greater than some design threshold, then you will still use the FSO link only. If not, then you will switch over the transmission to that of the RF link. That is what is the hard switching. So when you are switching over to that of the RF link, you will not transmit over your FSO link. Your FSO link will be disconnected. Okay, either FSO or RF. That is what is the thing in case of your hard switching scheme. Whereas in case of an adaptive combining, that is more of an optimal combining, where you give priority to FSO transmission. So your initial data transmission is over the FSO link. Subject to the fact that the quality is pretty good or the instantaneous SNR is greater than the design threshold. Suppose if the instantaneous SNR is lesser than the threshold, instead of disconnecting your FSO link, you still maintain the connection, you still maintain the FSO link connection, and parallel to this FSO, you transmit the same data over the RF. So the data, in case if there is a degradation in the FSO link quality, instead of disconnecting your FSO link, you will transmit the data over both FSO and RF by reducing the data rate of FSO link equivalent to that of the RF link. Because the moment you are transmitting over both FSO and RF parallelly, and if you are deploying a combining scheme at the receiver, say a maximal ratio combining among the FSO link and the RF link which you are receiving, then the data rate should be equivalent. So you give the priority to FSO, of course, with the high data rate. In case if there is a degradation in the quality, you don't disconnect and transmit only over RF. That is what is called as hard switching. So don't do that. Instead, you still use your FSO link with a reduced data rate equivalent to that of the RF and send the data over both FSO and RF. Okay, so that you can do an effective combining at the receiver that would enhance the reliability. This is what is called as the adaptive combining. So hard switching and adaptive combining, both techniques we have worked on it. So there are various channel models which you have considered. These are all the initial channel models which we have considered, because this is more or less like 4 years before. Now there are a lot of improvements in the channel models. As I have mentioned, this FSO is prone for at least 3 major channel anomalies. One is the atmospheric turbulence. Turbulence is mainly because optical signal is prone to this atmospheric turbulence, is mainly due to the variations in temperature and pressure in the atmosphere, because of which your the turbulence will be happening, and it impacts the signal. That is why it introduces fading. Basically, your turbulence only introduces fading, unlike your RF communication, where your multipath effects or multipath distortions is only will introduce a fading, which is called as a multipath induced fading. Your small scale fading especially is mainly because of the multipath propagation of wireless signals. So because of the multiple paths the wireless signal is taking over, the fading is happening. Whereas in case of your optical wireless communication, the fading is mainly due to atmospheric turbulence. And that is why they call it as atmospheric turbulence induced fading. And as I've already mentioned, why atmospheric turbulence? Like, what is an atmospheric turbulence? Mainly it is because of the variations in the temperature and pressure in the atmosphere that will impact your optical signal. So you have to model your atmospheric turbulence. One. Second major anomaly is the pointing errors, which we call. That is, pointing error is very simple. It is like when your transmitter and receiver is not aligned, okay, towards each other, and if there is a mismatch in that of the alignment, then of course the majority of the optical power is not going to be concentrated on your photodetector. There is going to be a mismatch or misalignment between the optical signal which is being focused on your photodetector, because majority of the optical signal, if it is being focused on your photodetector, that is, if your beam center exactly matches the center of the center of the optical detector, then there is no misalignment. If there is a mismatch, then there's going to be a drop in the optical received optical power. So which means eventually when you converted that into an electrical signal, again there will be a drop in the signal strength, right? So that is mainly because of the pointing error. So you have to model the pointing errors. This is mainly why you have to model this. Once you statistically model, then you can evaluate the performance of the system, right? That is why the importance of statistical modeling will come into the communication. So you have to statistically model. Statistically model means various channel anomalies such as atmospheric turbulence, pointing errors. This you would be modeling using various probability distributions. So how to choose the probability distributions? Depending upon the severity, depending upon the tightness of the model or the wide range of scenarios which it can model, you have to pick the appropriate probability distributions, right? These two are the major channel anomalies. That is the atmospheric turbulence and pointing errors in FSO communication. The third one is atmospheric attenuation due to fog. or any other climatic conditions. I'm mentioning fog because fog is a major threatening factor to the optical signal. So the attenuation due to fog is pretty huge. Your optical signal is being heavily deteriorated mainly because of the effect of fog, right? Fog and maybe fog, snow and smog, maybe those are the major the factors which leads to deterioration in your optical signal strength. Whereas your RF signal strength is being impacted mainly by the attenuation due to rain, right? So these are complementary. That is why, right, the real motivation behind establishing a hybrid link is because these FSO and RF links are complementary in nature. Whatever affects FSO will not affect RF, and whatever affects and vice versa. Whatever affects RF will not affect FSO to a greater extent, I'm saying. So even though rain attenuation is there in FSO communication, but it is not very huge. Okay, there is a rain attenuation. Attenuation due to rain happens, but attenuation due to rain is severe in case of your RF communication, unlike your FSO communication. Similarly, attenuation due to fog is more in your FSO communication compared to the RF communication. The fading is mainly because of atmospheric turbulence in your FSO communication, whereas in RF communication, the fading is mainly because of the multi-path propagation, right? Pointing error is a particular most important channel effect in your FSR communication, where pointing error is not at all there in your RF communication. In your RF based communication, you need not want to align your receiver towards that of your transmitter. No, there is no requirement there. That is why you can see these effects are complementary in nature. That is why a hybrid FSO RF communication became pretty much popular, right? So various distributions are available to model the atmospheric turbulence. The basic distribution is gamma-gamma distribution. Gamma-gamma distribution is nothing but the product of two gamma random variables. Product of two gamma random variable or gamma distribution. Hopefully, many of you should have come across. If some of you are teaching probability theory course, hopefully you should have come across gamma distribution. So this atmospheric turbulence is being modeled by product of two gamma distribution. That is what is named as gamma-gamma distribution, because that distribution seems to be a tight model for modeling your strong to weak turbulence scenario. Earlier works, you would also see log normal distribution also they would be using for modeling this atmospheric turbulence, and log normal distribution helps you to model basically a log normal distribution. It's a weak turbulence scenario. It models basically, right? Log normal, gamma gamma, and then people have come up with the Malaga distribution, which is a generalized distribution where it reduces to log normal as well as gamma gamma. After Malaga distribution, there are various other new distributions which were helpful in modeling atmospheric turbulence, which is called as Fisher-Snedeker distribution. And then the next one is very recently in the last year, it is IGG, inverse Gaussian gamma-gamma distribution. That is pretty inverse Gaussian gamma distribution. So IGG and then IGG, which is doubly inverted Gaussian gamma distribution. So which is abbreviated as IGG. Now all these distributions are heavily used. Maybe I will suggest we have written one textbook. I have written one textbook with the Professor Vivek Ashok Bora from IIIT Delhi, where we have discussed all these distributions and channel models along with the derivations exhaustively for FSO communication. So here in this work, we pretty much for the presentation sake, I kept it as gamma-gamma distribution. There are various key parameters which links to that of the turbulence, which is small scale turbulence large scale turbulence parameter, small scale turbulence parameter. There is a Rayleigh variance parameter. That Rayleigh variance depends on the height of the ground station height with which the HAPS is deployed, the angle of the signal propagation, that is this theta h and theta s, you can see, right, the propagation angle. So that angle, and then the severity of the turbulence, which is being measured using turbulence strength. This Rayleigh variance parameter depends on all these factors. As well as this Rayleigh variance is sitting inside your large scale turbulence and small scale turbulence parameter. Usually in your gamma distribution, hopefully if you would have been teaching probability theory, there are two parameters which will govern the distribution, alpha and beta. And alpha is I think one is the shape parameter, another one is the scale parameter, scaling and shaping parameter. So this scaling and shaping parameter is what is being mentioned as this alpha and beta. Right, so that is why, see, all these physical parameters are getting observed in these distributions. That is why it is useful to model these things. Similarly, pointing error also is being modeled. That is the radial displacement. Like as I mentioned, the center of your detector, especially your optical beam center, should match your center of your detector, right? If there is a displacement, that will, because it is more of like you imagine a circle, because center of the detector, center of the optical beam, it is more of circular beam if you can imagine like that, right? If there is a misalignment, then there is a radial misalignment, right? Radial displacement. That radial displacement is modeled as a point, like as a random variable. And the radial displacement means then you can resolve that radial displacement into a horizontal displacement and vertical displacement. Each of this can be modeled into a Gaussian random variable. If horizontal displacement and vertical displacement is modeled using a zero mean Gaussian random variable with equal variance, then the radial displacement, which is square root of x square plus y square, horizontal distance square, vertical distance square, the radial displacement, which is square root of this horizontal square plus vertical displacement square, that will be modeled using a Rayleigh distribution. If it is a zero mean Gaussian with equal variance, then the radial displacement can be modeled using a Rayleigh distribution. So there are a lot of distributions which we use and transformation of random variables which we would use in this case. And I will not go much into the detailed derivations. Based on these pointing error, turbulence distributions, we first obtained the PDF and CDF statistics of the instantaneous SNR, because instantaneous SNR statistics is very important, through which you can able to calculate your two important key performance metrics, which is outage probability and the average bit error rate or symbol error rate. That is why from this distributions of the individual channel parameters, we obtain the SNR statistics. From the SNR statistics, we obtain the key performance metrics, which is outage and average bit error rate. Maybe you can look into our papers as well as the book, which I will suggest towards the end of the presentation. So those things you can look into it, how to derive that and so on. Through this, as well as for the RF link, like it's a complementary RF link, we considered a shadowed Rayleigh distribution, which is also a very suitable model to model between the ground station and the HAPS. Okay, it's a shadowed distribution, or shadowed kappa mu is also another favorable distribution which you can consider. So with this, we could able to compute the outage probability of that system model, which I have shown, as well as the average symbol error probability. The detailed derivations I cannot go through now because of the lack of time. And maybe the detailed derivations are available in the paper as well as in the book. And for two of the schemes which we got, that is hard switching as well as for the adaptive combining scheme, we have exhaustively evaluated its performance over the outage probability, average symbol error rate, ergodic capacity, and so on. From the outage and average SCR, we could able to derive the important metric, which is the diversity gain. As you might be knowing that diversity gain is nothing but the slope of your outage curve or your average SCR curve, how fast your outage curve or average SCR curve is decaying. Because once you plot with respect to SNR, I'll show one of the plot, at least an outage or an average SCR with respect to that of the average SNR. As the SNR increases, your outage should be decreasing, as well as your bit error rate should be decreasing. That is what is the fundamental, right? So, but how fast it is decaying, okay, that is governed with the slope, right? If you have a very high slope, then the decaying nature would increase faster, right? So that is being decided by this metric called as diversity gain, right? And you can see effectively this diversity gain in some scenarios solely depend on FSO link, and in some cases it depends on both FSO and RF link. Okay, where you can see there is a term, there are three terms associated with this, like this alpha and beta. Needless to mention, it is the large scale turbulence and small scale turbulent parameter. This zeta square, which is being mentioned over here, that is connected to the pointing error severity, right? Pointing error coefficient. Higher the pointing error coefficient, lower is the pointing error severity. Okay, so of course, this diversity gain is linked with these three terms, and in some cases, there is +1 factor being added as well. That +1 factor is coming from your RF. Okay, from your RF link, that particular one factor is coming. Okay, so which is like both your FSO and RF link in some cases will decide the slope of your performance curve, right? So so various diversity gains under different scenarios have been derived, and some of the performance curves which you can see over here, This is with respect to various architectures comparison, where we have compared this. This is a dual hop scenario, and there is a hybrid link, right? The scenario which I proposed, where there is a ground station HAPS which is connected with the hybrid link, and the HAPS to satellite which is connected with an FSO link. This scenario, which we call it as a dual hop hybrid scenario, that we compared it with the dual hop FSO scenario as well as a single hop FSO scenario. Dual hop FSO means ground to HAPS FSO and HAPS to satellite FSO. Single hop FSO means directly from the ground to satellite it is FSO, right, without any HAPS terminal. This we have compared it with a lot of architectures, and we could able to effectively see that the dual hop hybrid link performs way better than that of the other architectures, such as a single hop FSO or a dual hop FSO based architectures, as well as if you have a good strength, good signal strength with respect to a backup RF link, the performance improves, as well as the right side plot shows with respect to the wind speed, the performance degradation, how effective, how your performance is depend upon your various wind speed. And we have also this is a plot with respect to how would you choose your design threshold when you switch it, because when the instantaneous SNR is lesser than some threshold, then you will switch to your RF link, right? What should be that particular threshold? So we have done some optimization and derived some closed form optimization expression for deciding the threshold values, as well as we have compared across the switching schemes as well. So over here, the right hand side plot, we have compared your dual hop hybrid architecture with the dual hop FSO and single hop hybrid architecture with respect to hard switching, as well as with respect to adaptive combining based scheme, where we can evidently see that a dual hop hybrid adaptive combining based scheme is performing way better compared to that of your dual hop hybrid hard switching scheme, as well as a single hop hybrid adaptive combining scheme is even performing much better than that of your dual hop hybrid hard switching scheme. So your adaptive combining based scheme is having a good performance improvement compared to that of your hard switching scheme, because adaptive combining scheme is more of an optimal combining scheme where you are not disconnecting your FSO. Instead, you are transmitting your data entirely over both your FSO and RF link, and you are doing a combining at the receiver. That is why it is one of the most optimal combining scheme, and that has also been plotted over here. There are various other improvements which we have done considering multiple HAPS and its performance, which is being published in one of the applied optics paper as well as in one of the ComsNet's papers and so on. So this you can refer to. So maybe I may not have time to go through it. Of course, there are also various works linking with this NTN with respect to RIS. Reconfigurable intelligent or intelligent reflecting surfaces, which is another potential technology in the future generation of communications. Hopefully, many of the lectures, they would have dealt with this, of course. So either they would deploy it over the HAPS in the horizontal surface, or they would deploy it over here, or as shown over here. So, especially this reconfigurable intelligent surface, basically it is the surface which reconfigures either like to steer the beam towards the intended directions with the better signal strength improvement. So to steer it to that intended user means you are improving the signal strength at that particular user, and you are not wasting your signal power towards the other directions where your users are not located. So that you can do it by having a control over the beam, and that beam control you can effectively have by deploying these intelligent reflecting surfaces. Instead of deploying these surfaces over the buildings, you can also deploy it over the UAVs as well as over the aerial platforms for effectively improving the connectivity as well as the reliability, right? So that is also another interesting areas. Of course, you can see various scenarios of this aerial platform such as HAPS and UAVs carrying this RIS for effective ground connectivity. And these are all some of the future work directions risks for instead of having an RF based RIS, optical RIS. It is also another technology or the technique where most of the researchers are working. And even we have built some prototype with respect to this optical RIS, a mirror assisted FSO based communication, where if you don't have a line of sight communication, we can position some mirrors in such a way that it effectively reflects back to that of the detectors, and we have even established a proof of concept for this hybrid sort of a connection, where if the FSO link is blocked, automatically it switches over to that of the RF link based on the bit error rate. Those sort of apart from keeping it in terms of the statistical modeling, we have also worked out some proof of concepts in our lab, and we have the setup over here. So in case if you're interested, you are welcome to visit IIT Indore as well.
Thank you very much, sir, for enlightening and impactful session. The upcoming questions are: what's the difference between 5G and 6G NTN architectures?
5G and 6G.
NTN architectures.
No, see, 6G is not yet standardized. Okay, 6G is in the study group only. In the recent releases of 19 and 20 and so on, the upcoming releases, they are working towards incorporating or working towards standardizing this NTN. So as such, we cannot say anything concrete on 6G, because 6G is in the study group stage only. It is not even in the working group. I hope release 21 onwards, 3GPP release 21 onwards, they are saying it would be upgraded to 6G, but nothing, no confirmed news. As such, the NTN architectures or whatever the information about NTN is available with respect to 3GPP is more or less which is connected with 5G only. Okay, so we cannot strictly say that this is 5G is NTN architecture and 6G is NTN architectures. No, we cannot say something like that. Whatever the two architectures which they have proposed, which is in the proposal stage, okay, it's not yet being finalized, that I have already shown, which is the transparent payload and the regenerative payload.
Thank you, sir. There is one more question from Deepa. Which simulator you have used in MATLAB, NS2
No,
or
this is
NS3?
no. This is not a network simulator, because I work in physical layer, and of course, it's easy to guess outage probability or a bit error probability, symbol error probability, ergodic capacity. So if these sort of metrics are there, it is predominantly a physical layer parameter. So physical layer parameter means we use either MATLAB, or if it is an advanced computation, which we use Python programming. Okay, so it is more of analytical derivations we do. We compute it using MATLAB or Python. Then we get the analytical plots. Then we do a Monte Carlo simulations to validate it. Of course, those who are working in performance analysis, they might be knowing that. Yeah.
So there is one more question from Rajneet. What additional features are expected from a laser as transmitter for FSO communication?
Not additional feature, nothing. Maybe a collimator or something to focus the beam towards the intended direction is what is being expected. Even in our lab, to establish an FSO communication inside our lab environment, we have not used any additional features. Simply a laser beam, of course, which is to be focused towards the intended receiver. That's what it is being.
So one question from Dr. Thilagam. For different architecture analysis, which software is used?
See, software or tool we cannot generalize. Okay, it depends on the need. See, for example, if you want to deal with the layer 2 and above, then you have to work on these NS2, NS3 simulators, as simple as that. Predominantly, if you want to work more on the physical layer aspects, then physical layer aspects, you have matured toolboxes available in MATLAB, or even the distributions and everything, you can model it using MATLAB. Nowadays, Python programming is also coming handy, where some of the computation which is slightly difficult in MATLAB, you can do it in Python, and you can do that as well. So these are all, of course, the minor tools which is available. Of course, if you want to implement some RF-based systems and signals, of course, if you want to use a software-defined radio, say USRP, then you have to use either NI's LabVIEW, or if not, at least the open source GNU Radio. So these are all the tools which we use: GNU Radio for implementation, then MATLAB, Mathematica to a minor extent. Nowadays, Mathematica we are not using heavily. We are using Python programming instead of MATLAB for doing some sort of a heavy computations, because say for example, for analytical derivations, you would derive these expressions in terms of various special functions such as measure G, Fox's H, and if there is a simple measure G and Fox's H special function, then you have a MATLAB function available. However, if you want to use a multivariate measure G and multivariate Fox's H function, then MATLAB till the current version of MATLAB may not be very supportive, where you have an equivalent Python programming to do that. So we use those tools.
Sir, how is propagation delay managed in NTNs?
See, that's why I'm saying now how it is being managed in the sense it is not yet being deployed, right? So that's what I would say that see propagation delay everywhere it would be there, even with respect to your base station to CUDU to 5G core, still you have various layers. Instead of it, if you can able to directly connect it to a satellite and come via your base station, of course there will be a slightly increase in terms of the propagation delay, but you have to see the application scenario. The application scenario with which the NTN is being targeted is not a mission critical applications where the delay is a sensitive parameter. Of course, for autonomous vehicle communication, autonomous vehicle and all that, you cannot, this is not a, maybe NTN may not be a very suitable thing, especially for remote user connectivity, ubiquitous connectivity. There the NTN's role is coming over there, right? So where the delay need not be much stringent, the delay aspects requirement need not be so stringent. Of course, compared to that of the regular network, maybe a slightly a higher propagation delay may be having, because your regular network directly connect to a 5G node B, whereas in this an NTN terminal is connecting to your NTN platform, then to a gateway node, then it is connecting to the G node B, then it is connecting to a core network. So there would be some increase in the propagation delay, definitely. But it may not be very high as well, and it may not, it is mainly targeted towards that remote connectivity. Okay, there it is being targeted where the delay aspects can be it can be compromised. Where the delay cannot be compromised, aspects such as ultra reliable low latency communication scenarios like autonomous vehicles, factory automation, there hopefully you will not be using your NTN. So you have to look into the scenarios where it will be useful.
Sir, how to understand read releases, WGN, start research, and connect with standards?
So read releases is you have various 3GPP documents available online, right? If you put 3GPP documents, now you will have inside that 3GPP website itself, you will have a lot of documents available. They have documented it perfectly, and various proposals which they are putting forward and the solutions which are available is also. Oh, I don't think so. The proposals you will get to see. Proposals will be for those who are attending the meetings only. And to attend those meetings, you need to be a member. Your academic institution should be a member. And there is a slightly a hefty fee available. There is a membership fee available. Or otherwise, you have to get into guest membership, which they also give for attending 1 or 2 meetings for 6 months or so on. They give you a guest membership as well. So there you can go and observe, but where you cannot propose something. So attending these meetings, you require at least a guest membership. For that, you have to get in touch with the Department of Telecommunications or your the standard the TSDSI, which is the standard body in India, right? Telecom Standard Development, I think Standards Institute or Authority, someone is there. TSDSI, which comes under the DOT. So that is the standards organization in India. So you have to get in touch with them. So DOT would be the proper organization to get in touch with them to get into the as a member, as an academic member or so on. And you cannot be an individual member in this case. I think it is more of an institutional membership. So as an industry or as an institution, you can get a membership. I don't think so. It is like an IEEE membership like that. It may not be that. It should be like an organization membership is what it is actually.
Normally, organization used to nominate.
Yeah. So, but as such, right, as Swaminathan, of course, yeah, from IIT Indore side, it would be nominated. Like from IIT Indore, if they're having a membership, either me or someone can attend without much of a problem. So that is how it is.
So, what is the maximum range in the case of FSO?
See, range is of the order of few kilometers. That is what is being tested. Of course, in India also they have tested in DIET Pune, Defense Advanced Institute of Technology Pune. They have tested with a link range of 3 kilometers to 10 kilometers. Also, they have tested it, but typically of the order of few kilometers. That's what it is being tested successfully, especially in the terrestrial range.
And it is also depending upon the applications that you are going to use it.
Yeah. Over the vertical atmospheric range, maybe it would be slightly more, because vertical, for example, ground to HAPS, you can still work on it because you might have a nice line of sight connectivity, and as the height increases, your distortions which keeps coming down. So They may be a slightly better range when you are over a vertical networks, whereas over your horizontal terrestrial networks, it would be limited of a few kilometers.
And one more question is there: how is resource allocation done for integrated terrestrial and NTN?
Oh, that and all is under the proposal. So I cannot because there is a lot of things over there. So as of now, only they are finalizing the architectures. So resource allocation is all in the researching stage, basically, because there is a gateway associated, then conversion into that. So that information maybe I don't know, or I don't have that information on hand, sir. That is what.
I think all the questions are answered. So I thank Dr. Swaminathan for giving his time, that in the weekends, and sparing the time with us, and giving a wonderful lecture. And of course, he has covered a lot of topics. And I hope that all the audience have have gone through it actually. And so thank you, Dr. Swaminathan. And
thank you, sir.